Welcome to another podcast. This episode, we're going to take a look at a couple of worked out examples involving the method of characteristics. I want to start with the following example. We're going to take a look at a inhomogeneous transport equation. So u of t plus cu of x equals 1. And let's suppose that the initial condition is, let's just say the cosine function. So cosine of x. So this is my IVP. So we're going to look at the solution of this IVP. So recall that the method of characteristics says that the solution du dt equals u sub x dx dt plus u sub t. That's just chain rule. And in order for this to match the solution for the transport equation, what we need is dx dt to equal c, because u of x times c needs to be dx dt, and we need 1 to equal du dt. So the system of ODEs that we have here is du dt equals 1 and dx dt equals c. Now, we've already solved dx dt equals c. This is just, remember, this is the observer moving at speed c, so at a constant speed. And in this case, this leads to the characteristic lines. So this is x minus ct equals arbitrary function, or arbitrary constant x naught. And du dt equals 1. This is equal to u equals t plus a, and u of x t equal t plus a if you are moving along a characteristic. So if you are on a characteristic, then looking at, let's say, u of x naught 0 is your starting position on that characteristic, then because t is 0, you get 0 plus a, and that needs to equal the value of u at 0, which is cosine, at the initial point x naught. And so the idea is that this arbitrary constant a is going to equal cosine of x naught. So in particular, coming back to u of xt, u of xt is going to be t plus cosine of x naught, but x naught is x minus ct. So the solution in this case is given by this equation. All right, let's do it again for maybe a slightly different example. Here we're going to look at a transport equation with decay. So we're going to have a decay term in here, and you'll see why it's decay when we actually solve it. So the example that I have here is, let's let u of t plus cu of x, and then we're going to add in the term plus a times u equal to 0. So in particular, this says u of t plus cu x equals negative au, and comparing that with du dt, this is our sort of our way to come up with the characteristics here. Dx dt plus u sub t. That suggests that dx dt has to be c, and du dt has to be minus au. So the system of ODEs here is of this form. Once again, observer moving with constant speed, but my function u, how it's changing as I move along the characteristic, it's actually decaying. What I'm noticing is the value of u decay as I walk along the characteristic. So it's no longer being held constant like it is for the transport equation. It's no longer not moving at all. Here it's decaying. So we have a decay differential equation, which is one of the easier equations from ODE to solve. And so this decay differential equation, if you just use separation of variables, whatever the case may be, has solution u of xt equals ke to the negative at. So this is what I meant by this being a decay, transport equation with decay. So dx dt once again is x minus ct equals x naught. And what we have here is if I make this an IVP, by adding the initial condition u of x0 equals, let's say f of x naught. So let's say I give you, well, let me back up a second. Let's suppose that we're told the initial value is u of x0 equals f of x. Then let's just have a starting point. So imagine this graph once again. So going back to the picture from the previous video, if you need to rewatch that. So starting at the point x naught, as long as I travel along characteristic lines, everything's going to stay okay. Now, suppose that we know that initially, everywhere along this, we have the value f of x. So at the point f of x naught, what we know is initially, we start with the value of f of x naught. And as long as we stay on the characteristic line, so on the characteristic, as long as we stay there, we know that that function must satisfy u of xt equals ke to the negative at. So in particular, u of x naught 0 is ke to the minus a times 0, or just k, but u of x naught 0 is f of x naught. So this tells me that my solution, u of xt, is of the form f of x naught e to the minus at, where f of x naught, I replace x naught with the characteristic x minus ct. So the point is, as long as we stay on this line, so this is the line x minus ct equals x naught, as long as we stay on that line, then what we notice as we travel with constant speed c along that line, we notice that the solution to u is decaying exponentially. Those two facts combined are enough to allow us to pinpoint exactly what the function u of xt is doing. And so in this case, this is our solution. All right, thank you for watching.